Log on, tune in, find out. Another good idea from Cambridge.
Speaker is Bradley Jones, well known to us all through coming from the SAS Institute and particularly associated with JUMP. And he's going to talk about definitive screening designs.
So like everyone else, I'm very grateful to be here and to have been invited to speak today about this subject, which I'm really very excited about. This work is joint with my collaborator and dear friend, Chris Noxheim, who is in Minnesota, and he's fully half of the team. So I'm going to talk first, trying to motivate the problem of screening that I want to deal with. I'll talk about the structure of the designs that I'm going to be advocating, how they're constructed, some of their statistical properties, an example or two, and if I have time, I'll show you actually computing these designs, how fast it can be, and conclude. So I'm not thinking about supersaturated designs. I'm thinking about the kinds of screening designs that are done very typically in industry. In the 1950s, I think Adelman wrote a paper that said something like, claimed in the introduction that perhaps 90% of all industrial experiments are two-level fractional factorial designs. And I suspect that that may still be the case. Given that these are the kinds of designs that people do, there are several choices that people have. One is the resolution 3 regular fractional factorial designs. And these designs are problematic because they confound main effects and two-factor interactions. And therefore, if you get a string of active effects from some analysis, you might have the embarrassing problem of having the three active effects be A and some interaction string, B and some interaction string, and C and some interaction string. And the C interaction string includes AB as the interaction in one of the interactions. So it's hard to know whether what you're observing is A, B, and C, or A and B and the AB interaction. Plackett-Berman designs are designs that have what has been called complex aliasing and therefore were criticized in the past because of that aliasing. And people said, well, at the time that they should only be used for main effect things and only if you were fairly sure that there weren't any interactions. I think Jeff pointed out very eloquently in his talk early this week that in fact the non-orthogonality of the main effects and the two-factor interactions is a blessing, and it does allow you to detect two-factor interactions in many cases when you run a Plackett-Berman design. However, the main effects and the two-factor interactions are correlated, and if you don't look for two-factor interactions, the main effects can be biased as a result of an active two-factor interaction. Resolution 4 designs confound the two-factor interactions with each other, so if a two-factor interaction effect turns out to be active, it creates an ambiguity where you don't know which two-factor interaction to assign the causality to. Although Roshan has written some very interesting stuff on how one might use a Bayesian method to deconstruct that. What's commonly done is that people add center runs to get an overall measure of curvature, and that makes engineers feel a lot better because they like that middle level. That's often the nominal level for factors, and they're afraid of an effect that goes like that, or an effect that goes like this, or an effect that goes like this. And if that were the case, then they're thinking that just looking at the endpoints would not really help them very much in terms of making predictions about how to control the process that they're looking at. So you can get the measure of curvature with a center run, but you don't know which factor or factors is causing the curvature. So the screening conundrum is that there are two models. Actually, there are a multiplicity of models, but there's a model that you're planning and hoping will be adequate to the task of modeling the system that you're interested in. But then there are also a number of other terms that may in fact be active, and typically the number of terms that you're afraid of is larger than the number of runs that you're willing to allocate to estimating them, so that in some sense every experiment's a supersaturated design, because the sum of the two models columns is larger than n. However, we're going to choose an n, and we're going to hope that a main effects model is adequate, and so we're going to fit the model with x1 here, and the result then is that if in many cases if there are some x2 terms that are active, then the estimates of the beta 1 vector will be aliased by this alias matrix that's shown. And so here's our Plackett-Berman design for a 12-run experiment. Actually, let's also add one center run. So a 13-run experiment with the Plackett-Berman design is the first 12 runs and one added center run. Looks like that, the alias matrix. And we can see that there are lots of 1/3, which Angela would like because that's sort of the functional maximum. But if only there were another 13-run design that had an alias matrix that looked like this, the same 13 runs, and if only that design didn't sacrifice very much efficiency for estimating the original parameters. Well, I have good news. So here's my wish list for a screening design. I want my main effects to be orthogonal. I want main effects to be uncorrelated with any second order effect, whether it's a two-factor interaction or a quadratic effect involving the original variables. I want all of my quadratic effects to be estimable. Therefore, I want a 3-level design. Engineers do, in fact, very much like 3-level designs because of that worry about this or this. And I'm afraid that you don't know, if you don't a priori know what the main effects are, you certainly don't know where the active part of the function is either, I don't think. You'd like the number of runs that you do to be order the number of factors, not order the number of factors squared. So if you actually wanted to fit the full quadratic model, the number of runs that you'd have to do would be order the number of factors squared. And you'd like the design to have some kind of good projective properties, and I'll talk a little bit about what I mean by that a little later. So there is some previous work on this. Jeff just talked about his paper in 2001, which dealt with 3-level designs with the notion of kind of dealing with, and you can correct me if I'm wrong, the idea of being able to sort of have a greedy response surface experiment where while you can't fit the full response surface model in all the factors immediately, if there are only a few active factors, then if you identify them, you have a design that will fit a response surface in that. Tsai, Gilmore, and Mead have a paper in 2000, and one of the designs in that paper actually matches up with one of the designs that I'm going to show you in this talk. And then Chris Knoxheim and I have a paper in Technometrics that talks about what kind of led to this design as a special case. So here's a structure that I think is really interesting. You'll notice that every element in this design is either a +1, a -1, or a 0. Now I know that Dennis can't count, but I think he can probably get to 3 from 2. So in each row, we have each row mirrored by the row, each odd number row is mirrored by the row below it. So the first 2 rows are mirror images of each other. And you can also see that the zeros kind of march down the factor settings matrix along the diagonal there. And then there's a final run that's all center runs. So this design, because of its mirror imaging, has all these wonderful properties. How did Chris and I find this design? Well, we were worried about the problem of aliasing and the multiple model problem, and we wanted to find a design that would minimize the aliasing of one set of terms that we define by another set of terms that we also define, minimize that aliasing in the sense of minimizing the sum of squared elements in the alias matrix, subject to a lower bound constraint on the D efficiency. And of course, this is minimizing a bias criterion subject to a constraint on a variance criterion. You could make the variance criterion be some other variance criterion if you wanted. So, and we got the design here as a result of that algorithmic search. And that's what we described in the paper that Dennis put up this morning. And our algorithmic approach gave orthogonal main effects plans for 6 factors, 8 factors, and 10 factors. But when we got up to 12 factors, even though we ran the algorithm 100,000 times, we couldn't find an orthogonal design. So there's something about the symmetry there that made it just impossible to find it using the algorithmic approach that we had. So enter Dennis Lin to the picture. He basically describes in a paper that's going to be published in JQT in January a way of constructing these designs where all of the main effects are orthogonal. And I thought that was really cool. So it uses what is called a conference matrix, and Dennis described that this morning, so I don't have to spend very much time on it. Essentially, a conference matrix is a matrix that has zeros on the diagonals, 1 and -1 off the diagonals, and which is orthogonal in the sense that C transpose C is a multiple of the identity matrix. And he also mentioned its other uses. So here's one of them, constructing a optimal conferencing electronics. So I thought I would put up a conference matrix just so you can see. I mean, it's claimed to be orthogonal, so why wouldn't it be a good design in and of itself? And I think that becomes clear when you look at just the first column of this matrix. It is true that all the columns of this matrix are orthogonal to each other, that is, that their inner products are 0. However, they're not orthogonal to the column of 1s. That is, they don't sum to 0. And so, as a screening design in and of itself, the conference matrix wouldn't be all that great. However, if you take a conference matrix and fold it over and then add a row of zeros, you get one of these other designs that have the nice properties. So the properties are, they are orthogonal for the main effects. The number of required runs is only one more than twice the number of factors. So if you have 6 factors, it takes 6 times 2 is 12 plus 1 is 13. If you have 12 factors, it's 25, and so on. So that's order the number of factors to create these designs. Unlike resolution 3 designs, the main effects are completely independent of 2-factor interactions. Unlike resolution 4 designs, the 2-factor interactions are not completely confounded with each other, although they may be correlated. Unlike any of the regular fractional factorial designs with center points, all the quadratic effects in these designs for every factor are estimable, although they are correlated with each other and also with interaction effects. And if there are 6 factors or more, these designs are capable of estimating all the possible full quadratic models. So no matter which 3 factors you choose, the 3-factor full quadratic model is estimable, and estimable fairly efficiently. So in a sense, if you were lucky enough to find only 3 active factors, you would have accomplished both screening and response surface in one go. So one thing you might ask is, well, how well can you estimate various effects, and are you going to detect an effect if it turns out to be active? So Chris and I did power studies of various types. This first power study is just looking at the power for detecting a single main effect, given that the intercept is in the model. And so we're comparing our designs with orthogonal designs. The orthogonal designs are Plackett-Berman designs for 6, 10, and 12 factors. That would be 12, 20, and 24 runs, plus, and then adding a center run. And the 8-factor orthogonal design that we chose was the 2 to the 8 minus 4 regular fractional factorial design. And you can see that uniformly the orthogonal designs are slightly more powerful for estimating fixed effects, the main effects of the model. That's because each column in our matrix has three zeros, whereas in the orthogonal design, each column only has 1 zero. And so there's more information about the main effects. However, these powers are quite high. You can see that if the regression coefficient is twice the error standard deviation, you basically have full power for estimating. Now let's look at power for estimating the quadratic effects. And it's pretty clear here that if the size of the effect is equal to the error standard deviation, you don't have very much power. But if the curvature is large, particularly if it's as large as 3 times the standard deviation of the error, then you will certainly be able to detect curvature of that size. Whereas in the orthogonal design, all of these quadratic effects are alias with each other. You can't pull them apart. And for estimating interactions, for the regular 2 to the 8 minus 4 design, all the 2-factor interactions are alias with each other, so you can't talk about power there. You can detect interaction effects from the Plackett-Berman type designs, and if you have all the main effects in the interaction term in the model, and then you pick any interaction effect, the powers shown here are the average powers over all the possible choices of the extra interaction effect. And you can see that these designs are actually doing better in most cases than the Plackett-Berman design in picking out those 2-factor interactions. So here's Here's an example with 6 factors and 13 runs. The D efficiency is 85.5%. The alias matrix, as I've shown you before, the top one's the Plackett-Berman design, the bottom one is the design that we're proposing. The column correlations, they have various flavors. The 2-factor interactions are either a quarter correlated or a half correlated, and the quadratic effects are either 0.13 with each other. They're all 0.13 with each other, and 0.46 between quadratic effects and 2-factor interaction effects. It is in fact possible to find and resolve more than one 2-factor interaction and quadratic effects in one of these designs. Here's an example with 12 factors and 25 runs and the same kind of plot. Notice the white up at the top there, that's showing that the design is orthogonal and that the main effects are completely uncorrelated with all the 2-factor interactions and quadratic effects. And you can see that as well, there are only a few possibilities for the correlations among the interactions. And as the design size gets bigger, the correlations between the interaction effects drops. Although as the designs get larger in number of factors, the correlations between the quadratic effects rises to an asymptote of a third. So here are the relative variances of the coefficients, and you can see that for if you were going to fit the model containing all the main effects and all the quadratic effects, the relative variance of the main effects is rather small, while the relative variance of the quadratic effects is about 10 times bigger. Still, all of these effects are much smaller than relative, they're less than half of the error variance, error standard deviation. So to recapitulate, these designs are orthogonal main effects plans. Dennis told you that they're only orthogonal when the number of factors is even. If the number of factors is odd, you can take the next larger even design and drop a column. All the same statistical properties apply. You just have a design that has 2 extra runs. So that's another way to handle that. Dennis said that they exist for even number of factors when the sum of the squares of, you can find sums of squares that equal the next lower number. You can also find them for even numbered factors where the next number below the even numbered factor is a prime number. And since primes are very dense in the first part of the number line, that means you see a lot of these designs for small numbers of factors. So these are all the wonderful properties, and here are some references. Thank you very much.
I have a simple way of obtaining 25 run or 12 factors with 3 levels. I'm not sure whether it can do all the things you want, but I'm sure most of it. If you simply take 12 run pattern matrix or Black-Berman design with column O+1 added, fold that over, you will obtain 25 runs with 12 factors, and add 1 row of O0. 25 runs, 12 factors. This is orthogonally strength 3, non-regular. So therefore, all main effects are orthogonal to all 2-factor interactions. And any 2-factor interactions won't be completely alias. in fact, correlation will be 1/3. And it seemed to me that the main effect also orthogonal to quadratic, because in quadratic square one column, you get column O plus 1, so it will be orthogonal. Now, if this is true, it will be better than your design, because you only have 1 0 in each column. You have 3 zeros.
But you can't estimate the quadratic effects. And so your design won't collapse to a design that can fit the full quadratic model. So that's a disadvantage of your approach.
So they cannot estimate in quadratic.
Full quadratic model, and these designs will estimate the full quadratic model in any set of 3 factors.
And
You made some comparison with the Plackett-Berman designs, but at those numbers, there's more than one isomorphism class. Would you get different comparisons if you use different Plackett-Berman designs?
I'm sure they would be a little bit different, but I don't think that they would be substantially different.
You said you can identify more than one interaction in your design, but your power studies were just for one interaction, is that right? So do you have any, off the top of your head, numbers for the power when you have more than one interaction?
I really was thinking about doing that power study yesterday because I was sure that question would come up, and I would guess that the power might be something like the power for one interaction squared. So if it was around 0.9 for one, it'd be more like 0.8 for two.
Thank you very much.